Welcome to SanfordFlipMath. This is AP Calculus, and we are working from the Finney, Demana, Kennedy book. We are starting section 3, which has to do with finding volumes, using calculus to find volumes. And as was the case with finding areas, we're talking about finding volumes of irregular shapes. Just a quick reminder that when we first started finding areas, typically what we would do is slice up an area into chunks, and usually what we did was we used rectangles initially, like this would be a left rectangular area method or approximation method, and something like that. And the idea was, as we used, so the concept was we would do a sum of our little change in x times height. So every rectangle was separate, a change in x times height, and that height was given by a y value. And we would add all of those up. That's what this sigma is, and we just threw that notation in there. Let me just kind of play around with this a little bit. And then the idea is that as we begin to get more and more rectangles, this change in x gets narrower and narrower. We have more things to add up, and this ends up becoming an infinite sum of infinitely skinny little rectangles, and that was the idea. And we would go maybe from A to B, and it became that. Well, we're going to do the same kind of idea with volume, and the idea is, if we have some volume that we're trying to find, and this idea, if it was just a little prism like this, wouldn't be a big deal. But the concept is that we will take slices of this, and we'll take lots and lots of slices of width dx, and the idea is I keep saying the idea is, sorry, if we know the area of this cross section, when we do the area of that cross section times the height or width of that cross section, imagine it flat like this, when we add up a whole slew of those, it's going to end up being the whole volume. Okay, so we're going to do a sum. We're going to add up basically area times dx, and that will end up being volume. Okay, so I need to kind of be able to picture things in terms of slices or cross sections. So here are some visuals to kind of picture this. My favorite go-to is a loaf of bread, and again, the idea is that we have all these different slices of the loaf of bread, and they all look pretty similar, but there are some variations. And so if you take one slice of the bread, and then if you knew this area and you knew how thick it was, okay, so, and then if you just added them all up, then you'd know the whole thing. Or here are a bunch of washers. Well, if you knew the area of one of those washers, okay, so all of this stuff, okay, so maybe it'd be the outside minus the inside or something like that, and then it has a thickness, then you would add those up. Same idea as the pizza boxes get smaller. If you had area times thickness, and so we're kind of keep going back to this idea of area of a base times the height, or, and for us that height is going to be the thickness, or dx. And same idea for cylinder, is just the area of the base will come from pi r squared, and so that's kind of going to there. All right, so that's the concept, and we're going to spend a lot of time on this, like a few days, just getting things going, okay? And so let's go on to the next thing. Now, what we're going to do is take a peek at number 2. This is directly from our book, the Finney, Demana, Kennedy book. It's going to be on page 407, and we're going to look at number 2. Okay, so give me a second. I'm going to kind of note down some of the stuff. Okay, so that was magical. You had no idea that I was even gone. I know that this looks kind of weird, seeing the x-axis go this way and the y-axis go this way. Okay, so I know that's kind of weird. And notice here's the y equals square root of x, and then here is the y equals negative square root of x. And so it's kind of weird looking at it that way. So I've kind of redrawn it like this. And now what they want us to do, okay, I'm going to pop back and forth quite a bit here, is they want us to look at the circles that are formed if I go, so this entire length is the diameter of that circle. This entire length is the diameter of that circle, etc. And so the circles are getting smaller down on this end. And so what we're making here is kind of like the shape of the nose cone of a rocket or something. It's kind of like a cone, but it's based on curves. So it's really not a cone. Okay. So just so we know what we're talking about. Okay. A lot of times what we will do is graph things like this. And so I want to look at one slice of this thing, okay? And it's going to be really important that we are able to draw these, and you might as well just start practicing now. This is going to be critical in understanding what's going on, okay? So the way this is going to work is I'm going to take one cross section, I need another letter in there, and I'm going to find the area. And when I say I'm finding the area, all I'm going to do is set up an equation for the area. Now, in this case, it's a circle. Okay, so they're trying to get us to make the equation of a circle. Well, the area of a circle is pi r squared. Now, the other thing that we need to see is how does this radius fit with what we're doing now? Now, we did do something like this back in chapter 5 when we were doing RAM and all that stuff, and now it's just going to get a little more serious. So where are the radii, the radiuses for these circles? So if I look at this circle, the radius is really that. Well, isn't that a y value? And isn't that this? Okay, so the area of one cross section is going to be pi times the square root of x squared, which I'm going to simplify it to pi x. Okay. Now, it turns out that this is all number 2 wants us to do. Well, we're going to do a little bit more with this. We're actually going to find the volume, okay, because ultimately that's what we need to do, okay? So it says in the directions, okay, way over here, find the formula for the area of the cross sections of the solid that are perpendicular to the x-axis. So they're saying the cross section itself, okay, like if I put a diameter through there, is perpendicular to the x-axis. So that's what we're doing here, is a cross section that's cutting across the x-axis. Okay, so what I'm saying, based on my little loaf of bread picture, if I added up the volume of every one of those slices, well, I'm telling you that the volume of one slice is the area of that cross section times the thickness of that cross section, and I'm telling you that the thickness is dx. So the area of one cross section times the thickness, this is now the volume of one slice. And what we're going to do is add up all the slices, and we're going to add them up from the x value 0 to the x value 4. Okay, and this is going to find the volume for that whole cone-ish kind of shape. Okay, well, so here we go. The rest of this is easy peasy. Antiderivative of pi times x. Well, pi is just a number, so this is going to be pi x squared over 2. And we will evaluate that from 0 to 4. Okay, so this is going to be 16 pi over 2 minus 0 pi over 2. Well, that was exciting. Okay, so 8 pi, whatever the units are, will be cubic units because this is a volume. Okay, and if there are no units present, I really don't need you to write units cubed, but I'm going to write them just so I remember it's volume. Okay. Let's do another one, and shockingly enough, I want to do number 2, part B. Okay, so part B for number 2, whoa, hello. That was apparently not the way to handle that. Okay, so let's do part B. And part B this time says we're talking about squares with bases on the XY plane. And they're giving us, so the base of the square is in the XY plane. So you have to imagine it's kind of coming out of the board. You know, if I go back, let's go back over here, go to the next one. Okay, so I have a square that goes across like this, and then it's going to come out of the screen. As you're watching this video, it comes out of the screen, and I can't really draw that in a very cute way, but there's the idea. And if I give it some thickness, okay, and again, you have to imagine this coming out of the board, and that's tricky, or out of the screen, however you're doing this. It's a slice, like a slice in the bread, or you could picture it as the axes are on a table, and then this board is sticking out from that. Okay, so this is one of the hardest parts of this topic is picturing what's going on. Okay, so the area of one cross section, it's just going to be, it's the area of a square. So it's going to be this distance times this distance. Well, if it's a square, well, from here to here, from here to here is the y value. From here to here is the same y value, only it's going down. So that entire thing, okay, I got enough braces there, is 2y, also known as 2 times the square root of x. Well, if that's true, then the side of this square will also be 2 square root of x. So the area then is going to be 2 square root of x times 2 square root of x, also known as 4x. If I'm going to find the volume, okay, so again, a reminder, the volume is just the area of that cross section times the change in the thickness, so it's going to be the change in x. The change in x is that thickness. Okay, so the volume will be equal to the area times the thickness, and we are going to add all of them up from 0 to 4. So 4x squared over 2, also known as 2x squared. Okay, so this is going to be 16 times 2 is 32, minus 0, so 32 square units. Okay. All right, so again, question 2, part B didn't ask you to do all of that. They just asked you to find the one, the cross-section area, but we needed to do that. Okay, I want to do one more. I'm going to do part D. Part C is kind of weird also, but part D is, I don't know, I guess slightly weirder. Okay, and the problem with part C and part D is they don't give you pictures, right? You have to make the pictures, and this is where it gets a little more interesting, is the word I want to use, but most people just think that means harder. Okay, so it says the cross sections are equilateral triangles with bases in the XY plane. So in other words, there's going to be a base of a triangle, and instead of a square, it's going to make an equilateral triangle there. And that's kind of goofy, and the thing that makes it goofy is we don't remember that. That's like a geometry thing, you know. Come on, Mr. Sanford, that was 3 years ago. What do you expect me to do here? All right, so what you have to do is imagine a bunch of equilateral triangles here, and the base is getting smaller and smaller and smaller as you get closer and closer to the end, and so it looks kind of like a little ridge or like a tent, you might say, kind of doing something like this. And it's taller as it gets wider because it's equilateral, and it looks something like that. So it's kind of cool deal, but how do you see it? That's the issue. Okay. All right. So the way this is going to work, pretty much all of this when we're doing cross sections here is, excuse me, you find the area of, in this case, what we need is the area of this triangle, which you know is 1/2 base times height, unless you remember the formula for the area of an equilateral triangle. And if you do, mad props to you, because most people don't. Okay, so let me just take you through a speedy revisitation of an equilateral triangle. And so if this is base, this is base, this is base, because it's equilateral, I need to do 1/2 base times height. Well, this is now base over 2. And what you may not think of off the bat is this is a 30, 60, 90 triangle. And so to get this length, it's the short leg times the square root of 3. So this is going to be base square root of 3 over 2. So the area of this triangle is going to be 1/2 times the whole base times base square root of 3 over 2, which most people would rather write as base squared square root of 3 over 4, or square root of 3 over 4 times the base squared. That is the area of that triangle. That is the area for this guy. Well, the problem is that what's the base? Well, thanks for asking. The base here is actually 2y, as we did, just like what we did in that square. So it's going to be 2 square root of x. So the area of a cross section is going to be that square root of 3 over 4 times the base squared. Well, as we just said, the base is 2 square root of x. So cleaning this up a little bit, this is square root of 3 over 4 times 4x, squaring both the 2 and the square root of x. So this ends up being x times the square root of 3, or square root of 3 times x. Just please make sure that x is not inside. Okay, so as we've said probably half a dozen times now, the volume is going to be equal to the cross-section area times the thickness of every slice. Well, and that thickness is dx. Okay, and then if we want the whole volume, what we're going to do is add all that up, again, from 0 to 4. Okay, so doing some speedy calculus here. I can bring the square root of 3 out, and I don't have to worry about it. Okay, so this is going to be equal to the square root of 3, and then the antiderivative of x is going to be x squared over 2, and we will evaluate that from 0 to 4. So this is going to be 4 squared, so 16 square root of 3 over 2 minus 0 squared times square root of 3 over 2. So I'll call that 8 square root of 3, and again, this is cubic units. Now, let's talk for just a second, I wrote squared, about why that's cubic, and we already know it's cubic because it's supposedly a volume, but remember what we're doing here. This is like unit for thickness, okay, and then this is the area. Well, so that's got to be square units. Okay, now how does that work? Well, back here, this was squared, so x itself was in units when, when we got this distance, that was in units, and then we squared it, so that's square units again times dx, so units cubed. Okay. All right, well, we're going to jam one more problem in here, and again, my concern is how do you draw it? How do you know what it's going to look like? So number 6 says the solid, we're supposed to find the volume of the solid analytically, and so again, what it says now is the solid lies between planes perpendicular to the x-axis at x equals -1 and x equals +1, and the cross sections are perpendicular to the x-axis between these planes, and they are squares whose diagonals run. All right, so that's a lot of stuff. What the heck does all that mean? All right, so I'm going to try and sketch some of this out. Now, first of all, that semicircle and that semicircle, well, you can play around with this, but both of those come from the idea of x squared plus y squared equals 1. If you subtract x squared from both sides and then take a square root, that's what you end up with. And so this is just this circle. Here's the positive version of that, and here's the negative version of that. Ooh, hello. Okay, that was beautiful. And then what it says, we're supposed to work with cross sections. They have to run perpendicular to the x-axis. Okay, and it says squares are diagonals. They run from the semicircle. So in other words, this is supposed to be the diagonal of a square. So there's going to be a square that does something like that. And this is the diagonal. Okay, all right, so that's the idea. Let me pop back over to a cleaner screen. Okay, so again, this is what it looks like. I have a circle, and this is 1, -1. This is technically a unit circle, but I don't really care about that. And again, I have a diagonal, and then this is coming out of the board, and this is going into the board, and this is now a square. Now, let's picture that square a little more straight on. okay? And this diagonal is this diagonal. Okay, now I guess the question is, how long is that diagonal? That's the first question. Well, it's from here to here, and then a mirror image of that down here. So it's twice whatever that is. Well, I would love to say it's 1, you know, that this is 1, but it's not. It's only 1 right here. So this is really whatever that y value is. And that y value comes from this. Okay. So this diagonal, I'll call it y, is really, sorry, I'll call it 2y. It's got to have a top half and a bottom half. Okay. So now the question is, how does that help me? Because ultimately, if I want to find the volume, remember the volume is going to equal adding up all of the areas times dx. Okay, so all of the areas times dx. That's what we're going to do, is add all that up. Okay, so I need the area of this square. Well, that's great if I know the side length of the square, but I don't. Okay, so what I'm going to have to do here is actually work on getting the side length from this 2y. Well, the easiest thing to do is remember that this is 45, 45, 90. And if this is 45, 45, 90, if I knew this, the side length, then I would multiply times the square root of 2. Okay, so the side times the square root of 2 equals the 2y. So that means the side itself would have to be 2y divided by the square root of 2, also known as square root of 2y, and you can play around with that and get that to work. Okay, so that means the side length of this square, is really just the square root of 2. It's not a negative sign, I was just using that to mark. Okay, so the square root of 2 times y. Okay, so the volume then is going to be, well, the volume, the area of one of these will be this times itself. The volume of one slice then will be that times dx, and I'm going to add them up, going all the way from this -1 to this +1. And that's supposed to be squared, sorry. Okay, so let me just remind you again. The area of this whole square would be this times this. They're the same, so that's the squared. Okay, and now it's just a matter of cleaning this up, and I'll try and move this along a little bit from -1 to 1. And when I square this, it becomes 2. When I square this, it becomes 1 minus x squared dx. Okay, and so I can actually take that 2 out in front, and the now let me write the step because I know somebody will freak out on me, and I don't want anybody to freak out. Now, so that since these are separate terms, I can actually just do this antiderivative separately. So the antiderivative of 1 is x. The antiderivative of x squared is x cubed over 3. And we'll evaluate that between -1 and 2. Okay, and we're almost done with this. It's just a matter of substituting at this point. Okay, so 2 times, well, why is that from that 2? That was not supposed to be 2. Sorry, got a little excited there. Twice the number, twice the fun. All right, put in 1. Put in -1, so -1. Now -1 cubed is -1 times -1 times -1. Okay, almost there. Okay, so there's a lot of sign stuff going on in here. 1 minus -1. -1/3 minus a +1/3 is -2/3. This is crazy. Okay, so this ends up being, that's 1 1/3 times 2. So 2 times 1 1/3, which is 2 times 4/3, which is 8/3. Wow, that was just joyously a lot of fun. Okay, now this is done, but before I leave this, I just need to show you something because I know you're going to all be mad about this. Oh, these are squares, never mind. I was thinking sphere for some reason. All right, so we're good. That's it. This is done. Um, the moral of the story, you're adding up cross sections. You're adding up slices. So think about it like a bunch of little bitty slices. Every slice has a thickness of dx, and all you need to do is establish how to write the area of a slice. Okay? All right, with that, I have gone mega long, but and this will not be the only video for this section. We'll be doing probably 2 or maybe even 3 more. So thanks for hanging with me, and we'll see you in class. Sanford Flip Math, we're out of here. Bye.